Good afternoon, everybody. Can you hear me? Almost, yeah. Almost. Well, I'm sorry I won't be shouting today. Maybe even coughing slightly. So thank you very much for coming. Welcome to this demo session. I'll be talking mostly about Kotlin Native today. And I mentioned quite a few exciting things yesterday at the keynote. And you can see that I have my iPhone connected to the computer for some reason. So so this is just for it to not slide off the table. So it's not development related. To recap, yesterday at the keynote, we talked about multi-platform projects and running Kotlin anywhere you can imagine. And in this picture, we can, of course, do all clients now. All technology I'm talking about today is only preview stage, so nothing's released. It's fairly early development stage. Things will break. I'm doing a live demo. It's a crazy thing to do at all, in such a big room especially. So expect the failures all over. So we'll be concerned with all 4 components of this application: server, Android client, a little bit less. We have a Kotlin native Android client, but it's like the least exciting part of it. iOS and even browser. So here I have actually the wrong slide, sorry. So I meant to have Kotlin native everywhere on this slide. And Kotlin native is the technology that translates Kotlin using LLVM to native binaries for multiple operating systems, including iOS, macOS, Windows, Linux, so on and so forth, and even the browser done the new way. So just to give you a general idea, the compiler backend that we have has excellent interoperability capabilities. It can call into Objective-C libraries. It can call into C libraries. It can make Kotlin libraries that delegate to C libraries, so to have nicer APIs, object-oriented and whatnot. So all that is possible. I'll demo a little bit of that today. And OK, it's time to look at some code. So I think I'll start with something the most exciting here, which is I'll unlock my phone. And here I have Xcode open. So this window is Xcode. And I can run something here, which will open the Spinner application on my phone. Can you see everything? Hopefully, yes. Now the application is running. Let's wait a little. So here is the app some of you have seen and probably even played. So I can spin the cube here. There are scores. 2 people were really actively DDoSing our servers, got really high scores. Good for them. One of them is a little bit ahead of the other. That's not the point. So this application is entirely written in Kotlin native. So here in Xcode, unfortunately, I can't zoom in on the project structure, but there is almost no C or Objective-C, just 2 very small stub files. And all the interesting stuff is going on in Kotlin code. So that I can open in CLine. OK, I have too many projects open. Just close the unneeded ones. The iOS one. So here's my CLine code, where I have main.kt file. And the interesting thing about this project is the external libraries thing. So let's look at what kind of libraries we have connected to this application. See, core data, core foundation. If you ever did any iOS development, you can recognize those names. So those are Objective-C libraries connected to a Kotlin project. And here is the structure of the project. So we have basically 2 classes. The interesting one is the view controller that can do things like game center, authenticate view controller, game center button, whatever. So these are parts of the application I had open in Xcode that are all written in Kotlin. So for example, when I say press the game center button, there is a piece of Kotlin code that gets executed. So it's pretty straightforward logic. I'm either show in the game center or authenticate. So basically, I'm pressing the button now, and this is what happens. The game center opens. I'm not sure I have enough internet for it to load, but it doesn't matter. So that's the overall structure of the iOS app. I have a Kotlin project that I can open in CLine, the CLine IDE we demoed yesterday. Then I can build it as a binary to be loaded by Xcode and deployed on an iPhone. I'll show you a little bit of what we can do with Xcode there. For example, I can actually debug. So I can, here I'm in LLDB. If you're afraid of assembly code, I'm sorry. I'll start with just showing a backtrace. We have some scary addresses here and everything, but it's actually not the point. I'll just set a breakpoint for some Kotlin function. And Kotlin functions in our binaries are prefixed with kfun. So here is my kfun view controller game center button pressed. That's the function I want to call. So here it is. Oh, I've lost it, sorry. No? Sorry. This tooling loves me not so much. Yeah, so this is asking the debugger to stop when I press the button. So I'll press it now. Oh no, I have to first let it go. Now it's going, and I've pressed the button, and here I am inside the game center button pressed. Lots of assembly code, but it's been generated from the Kotlin code you've seen, and we can see traces of that, because here we're doing kfun platform game kit something. So we're actually calling Kotlin wrappers for APIs of the platform. We also are doing interesting things here, like here's the show game center function that you've seen there in my CLine project. How do you like that? So I can actually look into the code. It's all there. My telemetry works. So Kotlin runs on the iPhone. It's a real LLVM binary. And all that code comes from the CLine project. So, OK, I think here we are done. I'll just let the project stop for a while. And now that you know that I can actually write something and deploy to the iPhone, we'll look into simpler things. So you see that here I have to employ two IDs to do something with the iPhone. It's because all the technology is very early stage. So actually, we have like everything in pre-alpha. So I have to juggle my tools here. But the good thing is that I can actually open a storyboard for my application in Xcode and edit the UI in a native way, which is great. So now I'll step out of the iOS world, probably the most exciting but not the easiest tooling, and look at some simpler things. So suppose I want a simple program. Yeah, so it's like a bit complicated hello world that does 10 iterations of a loop and then prints a greeting and a number. Let's put it this way. So if I run it, it creates a binary for me. And you can see that it's using CMake. So I'm now inside a CLine IDE with the Kotlin plugin installed. And here is my absolutely natural Kotlin program with no special imports or something. I have my external libraries, of course, but those are fairly transparent. And actually, here I have like the entire platform. And here's the output. Everything's fine. I want to demo some debugging in the CLine, because that's a little bit more usable than Xcode with the command line for LLDB. So here, I can step through my loop, and I'll show you the console that it actually does what it's supposed to. So my 1, 2, 3 all come in the right order. I can see the local variables, which is great. We'll work more on displaying the values properly, because currently it's just Objective-C headers, but still, you can do things there, which is nice. So this is the desired user experience for all native code we're writing in Kotlin. By the way, do you have any questions at this point? No? Go ahead.
Do you expect us to work in C-line, or later it will be like in
Oh, that's OK. The question is, do you expect us to work in C-line, or it will be later something else? So I'm not making any announcements here. So for now, we expect you to work in C-line using the Kotlin native plugin. We'll probably extend the presence of Kotlin in other JetBrains IDEs. There may be other developments. I'm not telling you more. Yeah, but for now, your workflow is you install C-line, you install the Kotlin plugin onto C-line. So you use CMake as the project model. Here's the CMake file for Hello World, pretty straightforward. So here is the Conon-C executable. Conon-C is the internal code name for Kotlin native. This is how you build the project. And the simple one is fairly straightforward. And so far, you do this workflow, and I'm not telling you anything else. Any more questions? Go ahead. Oh, I'll show you that a little later. Yeah?
What's the question?
Oh, sorry. Yeah, the question was, can I import things like OpenMP and stuff like that? I'll show how you import libraries just in a second, actually. So we're more or less done with the Hello World app. And what haven't I? Oh, yeah. I'll probably skip looking into the binary, because the assembly code feels scary. And let's look at the actual demo that we are running with the Spinner app. So the Spinner app consists of those multiple components, right? So here, where's my slide? Here, I have a server that's running Kotlin native using the micro-HTTPD library written in C. So I'm delegating to that. And I have actually a browser client that's also doing Kotlin native through WebAssembly. So I'll be running those two. Here is my server. I'll run it from C-line. Here it is, already started. I had it compiled in advance, so that's not the actual responsiveness of the toolset. I need to start the server. Done. Now I can load the WebAssembly page that's drawing the scores for us. It's all zeros in the debug session. And this is what those DDoSing people were doing. Now I'll click through just calling the right URL. Now I have one somewhere. Not so exciting, so I'll go and do something more close to what they did and just do this. I'll be clicking a lot. So every curl call from the console has a different ID, so it's all different teams, so it will more or less level out. So the interesting thing is that this page is not actually running JavaScript. It's running WebAssembly, which is the new, not released technology, not by JetBrains, by major browser vendors, that runs LLVM binaries, more or less, in the browser. So basically, you take a wonderful virtual machine that you have for JavaScript, like in Chrome, it will be V8. You cut off the JavaScript part, because you hate it. And on this, thank you. So on this wonderful runtime, you can run very efficiently your code that's been initially compiled like native code. So that's WebAssembly, and we support it now. So browsers do support it to some extent. And I hope that in a couple of years from now, if everything goes well on the WebAssembly side, we'll be able to skip JavaScript altogether in the browser and finally get rid of this wonderful legacy that we've been stuck with for like 20-something years, I think. Yeah, and I want Kotlin to be really present there. So that was the demo, and now let's look at the server app, what it's built of, and what components are there. So I have my CMake file here. Server is a big thing, so there is many dependencies. And if we look under external libraries, we'll see not only standard Apple libraries for Mac OS, but also micro HTTPD, for example, the web server written C, or SQLite. So those things are connected to a Kotlin native program through our tool called cintrop. So this is how we call it here from CMake. So the idea is you simply take a header, C or Objective-C header, and you generate the layer of Kotlin code that just makes that C API into a Kotlin API, basically. You don't ever see this code as source code. You just compile it right away to a binary. Or, like, I think now we don't even generate the text at all. We just emit the binary right away. And sorry. And this is roughly what you get. So, like, you have a number of declarations, just normal Kotlin declarations for C functions that were in that H file. Makes sense? Yeah, so I won't be explaining those interesting spells we're doing here. C values ref, so on and so forth. The introp is a very interesting story, but I won't be getting too deep into it. Another thing I want to show you is this def file here. So a def file is just an instruction to the cintrop tool, what header to take and how to process it. So this particular one is not very interesting. So I think SQLite will be, no, SQLite will be scary, so I'll do micro HTTPD. It's actually all the same, just fewer lines of code. So here for micro HTTPD, a C library for HTTP servers, I declare what my package is going to be, what headers I need, what dependencies I have, and normally such libraries depend on something like POSIX. Then maybe not all binaries for micro HTTPD have all the functions that the header has. That's normal in the native world. I think it's crazy, personally. I want to get rid of this, like, here is the header, it declares the API, but here's the binary, it doesn't have some of the API. If you run it, well, you can't run it, but if you compile against it, then you don't link. Like, linker tells you there's no symbol. I personally want to get rid of all this, and we probably will. But here, the point is that this function is not present in some versions of the library, so we exclude it, not to require Kotlin to link with it every time. And so this is how all the native dependencies are connected to the native project. So many libraries, many dependencies first. Then we can write wrappers for those libraries. For example, if you want an API of something, it'd be nicer, like, I don't like curl as it is in C. I want curl with K for Kotlin. So I can write my own wrapper. I think I'll find it right here. Curl KT. This is the right one. Yeah, so it's importing the libcurl APIs and does some nice things to wrap it for to be a proper Kotlin API, proper Kotlin class when you create a URL instance instead of like calling only into C functions. And then you can build that into a library and also connect to your project. And you end up with a executable that's a standalone binary, everything statically linked into one executable. You have your libraries here, dependencies, all those either interop or your own wrappers that you've declared before. And there you go. Actually, this project builds multiple executables, but we'll only look at this HTTP server one. Make sense so far? Any questions? OK, the question is, how about Objective-C interoperability? It's kind of the same. So this particular this particular project is good for both Linux and Mac OS, so it doesn't do any Objective-C. But in the same way, our iOS app calls into Objective-C libraries. There is, of course, a bit more of the API matching, because Objective-C has classes in some way, a weird way, admittedly. So we're doing all those more fancy stuff, and will be more work there, but it exists, and the iOS app is actually running all that.
It's the same utility-C interrupt, or it's an OpenGC interrupt?
Oh, this is something I don't remember. Yeah, it's the same command line tool, probably different code in it, but yeah. Another question.
What about Swift interrupt?
Haha. OK, question is, what about Swift interrupt? Swift interrupt is in progress. We'll have to do more work, because Swift is like much more statically typed. You don't do many hacks that are possible in Objective-C and Swift. So we're looking into that. But you can, I'm pretty sure you can already call Kotlin functions from Swift, passing collections naturally back and forth, which is already very good. All right, so this is the structure of the project, and now let's look at the code. So here I have my, well, it's actually a lot of code, because the server is doing, security, stuff like that, tries to fight the DDoS attacks off, fails to do it. Yeah, so anyway, it's quite a bit of code. But it's nothing really magical. Simply calling into the APIs that are provided by native libraries, for example. Here's my micro HTTP calls. Connection, whatnot, response from buffer, headers, whatever. And I can actually run this and debug. Am I running anything yet? Yeah, I am. So I'll stop this. And I'll debug this, putting a breakpoint here. This is, yeah, it's working. Yeah, so on every request, this function is called, and we can see that CLion can actually look into the debug process and show you some very interesting numbers here, which you don't understand because these are raw memory addresses. But still, you have the local variables. You can debug through creating objects there, and here is your URL, for example. Now we know that my WebAssembly page is pinging the server, asking for stats all the time. So this is where we are stopped at the breakpoint. Here's the session object right in the editor. You see the color, the name, unknown, the password, right in the debugger, very secure. And so on. So you can actually go through all this, and it's a pretty natural experience. We can actually even render null for you. Sorry. Yeah, so this is what you can do with this code right now. So let's look a little more into other things you can do here. I would like to show you how you test this code. So here's my server test class. And here, it's actually interesting because this is a bit of the interrupt story. Sorry, not interrupt, of the multi-platform story, as well as just Kotlin native. We have those Kotlin.test annotation here. Before each, after each. I hope I can navigate to that. Oh, yeah, I actually can. That's wonderful. OK, that's decompiled code, but still. Yeah, so all these are defined in the Kotlin test package that's available for all platforms. So it's not like JUnit or something, although it maps to JUnit on the JVM. So here I have a task class with initialization. Before each, I create my database, so on and so forth. I remove the database after each test. And then I have a bunch of test methods. So each test method has a lot of logic in it with JSON, whatever. So this I can hopefully run. Yeah, here it is. I can run and see that all my tests are good. And if I change something in assert equals I'll, don't know, do something bad like this. I can see a test failure. And now you can see the compilation speed can be improved. But it's actually sucking in very many dependencies, so it's understandable that it has to do some work. Meanwhile, any questions?
What about exceptions?
The question is, what about exceptions? Actually, we'll see what about exceptions right away. Here we go. It's a stack trace. So here you have your exception with the message. And here is the actual trace. Kotlin throwable, error, assertion error, asserters, whatever, test runner, and here's my main. So I think we're doing pretty good here. So server test, here is the actual line of code that's, that belongs to, oh no, not that. One of those is the, yeah, so this is the actual line that caused the exception. So you see that the console parser doesn't recognize those stack traces yet, but they are there. All the information is present. OK.
The 1879, is it the line?
Wait. Yeah, I think it's a binary offset. So the lines must be not available, or no, because these are not lines. The actual line is something else. It's this one, 81. If you see an 81 there, that's a line. No, it's not there. Sorry. Lines are not printed yet. Well, but the good thing is that you can actually do all the debugging and inspection with standard tools. Like you've seen that on iOS, I was debugging with LLDB. It's like a vanilla tool where we're not providing any special things to do that. So it's a standard binary with the standard dwarf debug information, which is a little bit of trickery going on because we have to fit all the Kotlin power into dwarf. That's never been designed for Kotlin. Well, dwarf is actually extensible, so we did our own extension. And LLDB can do that. We're working there on making more things available. But it's still pretty good. So here is my test. It failed in the proper place. Show you the stack trace. And how cool is that? Questions? Yeah?
Garbage collection?
The question about garbage collection. So, OK. So I'll be digressing a little bit. So the memory management story for Kotlin Native is a very interesting journey into many, many options. So of course, we could try to emulate the JVM, for example. Tracing GC, stop the world, whatever. And that's a possibility. That's a lot of work. And that's all the implications that tracing GC has on the JVM. So it's something we're trying to postpone as much as we can. So currently, we have a different schema, a little bit more like what Swift does and Objective-C. So we have reference counting. So far, it's a lot simpler than what Swift and Objective-C do. Reference counting with more or less isolated threads. So currently, we're not actually sharing memory between threads at all, which makes memory management fairly straightforward. Very convenient, isn't it? And here you can see, for example, that I have to say init runtime if needed, which means that I have to reinitialize my runtime structures on every thread. It's just because threads are not very native to Kotlin Native yet, but we're working on it. So I can tell you what the final memory model will be and what memory management mechanisms we'll settle on. But our goal on iOS is interop with Objective-C and Swift. So there we'll be doing something compatible with ARC, automatic reference counting mechanism for Objective-C and Swift. Our memory model without that can have different options. We're looking into that, experimenting. We'll see how it turns out. So this is what you call a technology preview. More questions? OK, the question is, how about calling Kotlin native code from C? As far as I remember, we currently don't expose a C ABI, but we already expose either Objective-C or Swift ABI. Is that correct?
Well, it's half correct, and also, if you think about this code, it's already Kotlin call from the C because.
Okay, yeah, I'll explain. So what Nikolai says, Nikolai is actually the person leading the native project. So it's complicated, but this code is actually called from C because we have passed a callback to a C function. So if you see where this is used, it's here. So I have my mhd start daemon, which is a C function, and I'm passing callbacks to it. So here is a Kotlin Lambda turned into a callback callable from C, which it actually is. And here is a different form. It's just a function reference, also turned into a static C function and called from C. So it's a callback, and up stack there is C code. So it's already working that way. So the ABI is not quite there, but this is already working, of course, because otherwise we wouldn't be able to do any round trip with the C code. More questions?
Passing structures by value, just another.
OK. Yeah, so the question is passing structures by value. We have interop, special interop facilities for doing this, like opaque types. So you can do back and forth with the native memory. The interesting part would be defining those things in Kotlin to be passable by value. And this is not very smooth yet. We're looking into it. So basically, what I would love to see there is a proper value types story for Kotlin, where you can define something that's always passed by value, that can be treated as a value in all contexts. So to make it sane, we'd actually have to make those things immutable. And this kind of doesn't very well coincide with the interop story, because when you pass a structure to C code by value, pass a structure to C code in general, you want it modified in many cases. Like you would often pass a pointer to a structure, to a C function, so it writes some data back to the structure. And this is not something you can make sanely for a managed language. So it's actually a complicated story. So why, for example, Java, while thinking on Project Valhalla, has immutable value types. So the goal for the JVM is to introduce compact storage with no extra links in memory, no extra references. So it would be nice for them to have something stored by value. And they're doing this immutable. Why? Because, for example, C# has mutable structures. And it's so much of a pain to manage. So we actually looked into how it worked on CLR and decided never again. So thanks, CLR people. You've been there. You've tried it out. It doesn't work. We're not doing that. And I have the same mindset as the Java people. So we're also looking into making immutable value types for Kotlin. So this will mean passing things by value around, but not mutating them on the other end, which is half of the story, because interop wants more. And for interop, we have those opaque types, and it so more or less works already. It will be polished a little bit, probably, but there we are now.
How would that work for JS?
Question, how would that work for JS? For JS, we don't have that problem, actually. So when we are compiling down to JavaScript code, we're going to have a value type declared in Kotlin, but actually compiled to a JavaScript object. So that Kotlin code just is not allowed to modify it. JavaScript code can hack on it, of course, like C code can hack on any memory you are exposing, of course. Yeah, but generally, if you don't have anything but JavaScript objects in the JavaScript world, there's no way around it. You just pass around your JavaScript objects. There is an option of allocating an array, a typed array of ints, for example, for compact storage of an immutable object. But then you can store references there, so on and so forth. So there are issues. So probably it will be just plain JavaScript objects. More questions? OK. Question, does Kotlin Native support coroutines? The answer is yes. Every platform we're working on supports coroutines already. And in this sense, Kotlin Native is kind of in the same mark it as Go because Go is a language running natively, compiling to standalone binaries and being very asynchronous with Go routines. So Kotlin is there, more or less. Well, we're not production ready yet, but still. We compile to native binaries, to standalone binaries. We have coroutines. And so we will be able to compete there. And actually, this particular server is a good example of a microservice written in Kotlin. OK, the question is reflection. The answer is yeah, so reflection is a big challenge, of course, in the native world. I think we'll eventually support limited reflection, where you can mark up some of the classes in your code base, opt in for reflection, because otherwise it's like huge binaries, very slow code, and very little benefit. So probably sometime later, we'll have opt-in reflection. Question, can I create iOS frameworks with Kotlin? Answer is yes, and this is how my Xcode demo works, actually. So this project has a framework compiled by Kotlin C connected to the project. No? It's not true? No? Oh, that was the plan. Sorry. Oh, sorry? Yeah, so I can see, you can hear Nikolai, so I'm taking this back. So I was running too quickly ahead. So that's the plan, to have the frameworks connected here. And here we are actually playing some more nasty trick with Xcode. So I was just dreaming that we're already there. Sorry, not there yet. OK, you, then you. Mm-hmm. Oh, I can hear you, sorry.
Is there any plan to bypass the JVM bytecode and compile directly to?
All right. The question is, are we planning to bypass JVM bytecode and compile directly to Android runtime? You mean Dalvik bytecode? Not really, because the tool chain there is good enough, so there is no big point in doing that. But we can compile natively for NDK, and we do that. So the Android version of the Spinner demo does that. Question in the back.
When will Kotlin native work with multi-platform projects?
OK, the question is, when will Kotlin native work with multi-platform projects? So yeah, it's a good point. Kotlin native currently doesn't work with the tooling support for the multi-platform project. So the compiler itself supports the necessary keywords, so you can have and expect an actual things there. But the Gradle plugin is not there. We're working on it, hopefully soon. And actually, this project is multi-platform in terms of it has common code here, like client common. This is code shared between multiple clients. And like different clients can provide smaller, so they link to a client common via symlinks here, just because the tooling is not there yet. So these are things actually shared by multiple clients, and here is common code specialized for different platforms. So the technology is there, the tooling story is not finished yet. Oh, so many hands. Sorry, I'll go there first. Oh, OK. So the question is, will we support compiler plugins? The answer probably yes, but we're not ready yet. OK. Question, will there be two different heaps, one Java heap and one C heap? The answer is, if you mean that you're running a Kotlin native code inside a JVM process, that's a very interesting use case. Like you write a project entirely in Kotlin, but part of the Kotlin is compiled to Java bytecodes, and the other part to native, and we may be able to omit the JNI links between the two. That's possible. Then there will be two heaps, yes. But it's not a high priority thing to do this. Yeah. Yep.
So do you have a problem with now inlining lots and lots of native code rather than just little nice Java bytecode?
The question is, do we have a problem inlining native code compared to Java bytecode? We are actually inlining on the internal presentation of our compiler. So we're going to migrate all the compiler backends onto this infrastructure later. So now the native compiler infrastructure is the most advanced among the 3 compilers we have. So I'll migrate all onto that. So inlining is not like the very bad. It's not very bad problem there. It's all right. Artem?
So in multi-platform projects, we expect to write common code thinking about reference counting instead of like Java.
OK. Question is, if we're using Kotlin native in multi-platform projects, will we be expected to write common code thinking of reference counting? The answer is, well, try to avoid this. So currently, our reference counter has cycle collector. So you have your normal reference counting experience, plus you can run cycle collection so that you don't have to declare weak references all over the place. If that's for some reason not workable, so far it is, then you'll have to resort to explicitly marking weak references across the code base. Yeah. Questions? More questions? Yep. Question is, how do you distribute the Kotlin native libraries? I believe I have something to show you here. So, will I be able to find my klibs? Yeah, so an executable is just a kexe file, which is straightforward. And then there are, I won't be able to find them now, but we have a format, the binary format, called klib, which is a Kotlin library basically containing even different platform implementations of the same library. So it's supposed to have a single API implemented for different platforms, so you don't have to like install this library for this particular architecture in your machine when you're cross-compiling. So that will also contain the metadata for the declared functions and classes and so on, and the the documentation, so on and so forth. So that is like the jar of Kotlin ecosystem. We'll probably make klibs available not only on Kotlin native, but somewhere else. We'll see how that turns out. That can open very interesting opportunities in multi-platform programming. Our time is running out, so I'll summarize with the same slides I've been showing. So with Kotlin native, we're able to actually make Kotlin available anywhere you need it. And this demo is showing Kotlin native on every platform imaginable, but it doesn't mean we intend to replace everything with Kotlin native. Like, should we replace JVM with Kotlin native is an open question. Some cases probably yes, some cases probably no. So we'll yes. Some cases probably yes, some cases probably no. If you're running command line tools, obviously Kotlin native will start faster, so you don't want to use JVM there, and we'll use native. If you're running like a huge server, it may be better to use the like long optimized JVM instead of Kotlin native there. It's up to the use case. So all platforms stay. We're doing JVM, we're doing JS, we're doing native, and it's a very exciting multi-platform world. Thank you very much for your attention.